I'm going to talk a little bit today about zinc stable isotopes, which is very exciting, just to get a little bit out of the boring land of C3 in Pleistocene Europe. So yeah, herbivore paleoecology is going to be mostly the theme. So we kind of have this problem of like, normally we have this kind of nice separation, C3 plants, C4 plants. Often we can link it to a grazer-browser distinction because C4 plants, as we've heard many times today, are often mostly grasses. But in Pleistocene Europe, we don't have those. So we're kind of restricted to C3 plants. And there are some differences in C3 plants to do with kind of like canopy cover, more open environments, changes with temperature and water availability, things like this. But you have to keep in mind that often the changes are quite small. And because there's quite a lot of different drivers, it's often a bit hard to tease apart what's going on and how it relates to things like feeding ecology in herbivores. So you often end up with something like this, where you have kind of like nice diachronic data that all looks the same, and it's all like within 1 per mil. But on the other hand, in the European light Pleistocene, we would kind of really like to know more about what the herbivores are doing in terms of the feeding ecology. We have these really dramatic environmental shifts between steppe environments and sort of like boreal forests. It's sometimes quite cold, sometimes much more warm. This happens very rapidly. And it would be really interesting to know how different species respond to these environmental changes, how that relates to human subsistence, what we can know about the environment. So lots of things that we would like to know more about, and carbon isn't really helping us enough. So let's talk a little bit about zinc. So I think most people have kind of skipped the intro a little bit, but since it's an isotope that I think most people don't know too much about, I'll give a bit of background. So zinc it's not truly a transitional metal, but we can think about it chemically mostly about a transitional metal. It's quite similar. It's sitting up there in the periodic table, and we have seen from studies, from other Pleistocene studies, that it does preserve quite well in dental enamel. For other things, dentine and bone, things are not looking great, but for dental enamel, it looks to be actually very well preserved, which is nice. And if you have questions, I can talk more about that later. So we can use it for archaeological applications. And so let's talk a little bit about, okay, what's going on with zinc? And so one source of variability that we have in the food web has to do with where's the zinc coming from? And as with many dietary isotopes, it's like you are what you eat, kind of. So this plants uptake zinc from the soil. So there is also a bit of an influence that we have to think about sort of like biogeochemical cycling in the soil, the source of organic matter, things like this. It's uptaken through the root system by plants. And the biological function mostly has to do with building of proteins and cell walls. It's actually very, very important for plant growth. It's one of the, zinc availability is one of the most major limitations for plant growth. And then herbivores get their zinc from the plant food and carnivores from the prey. So it kind of transfers up the trophic chain like that. And then we also have biological fractionation in zinc. And this is a bit different than what we have in things like nitrogen. So what we mostly see is that there is basically a separation of different types of tissue. And so mostly what we see, so this is all data from controlled feeding experiments, is that soft tissue like muscle or kidney or liver tend to have lower delta 66 ZN values than other tissues. Something also to note is that, for example, in bone, it tends to have slightly higher stereoisotopic ratios than soft tissue. And so this actually leads to currently the most common application of zinc stable isotopes is for trophic level reconstruction. But something to note is that it goes the opposite way, because essentially if you have animals, carnivores, that are consuming prey, mostly what they eat is soft tissue, which has a slightly lower isotopic ratio. So you have kind of a declining trophic level that goes the opposite way of the nitrogen. But we also see variability in the plant biome. And the biggest effect that we know about at the moment is that there's essentially a translocation effect. So roots tend to have relatively high stable isotopic ratios, and then as like the further you get up inside the plant, just kind of distance-wise, the lower your isotopic ratios are going to be. It's not quite clear what exactly is the mechanism for this, but we see it very repeatedly in different plants, and we also see it between different types of plants that have different growing height. So in that case, grasses would have slightly higher values than things like tree leaves, stuff like that. So what about herbivores? So we're kind of getting more into the things that are actually interesting. And so I'm going to talk here a little bit about an example. We're talking about the site called Ranis-Ilsenhöhle. It's in central Germany. It's a middle to upper Paleolithic transitional site. I'm going to skim over the archaeology a little bit because all of that is still unpublished and forthcoming. And also, I don't know, it's not, let's focus a bit on the zinc. That's kind of the thing that I want to talk about the most. But just to know a bit the background, so it's a central German site. A lot of the archaeology, so the archaeology is most known for, it's called this LRJ that has a very long unpronounceable name, but basically what you have to know, it's this middle to upper Paleolithic transitional phenomenon that extends basically from Central Europe and Poland up to Britain. And the data that I have, it's really mostly horses from different levels. Something to know, and I think Rhiannon will commiserate, is that some of this is from a really new excavation that finished only in 2022, but most of this is from a 1930s excavation. So in the end, what I did is radiocarbon date all of them because the documentation of the 1930s was a nightmare. And then on top of the horses, which is 16 total, I also have zinc stable isotope data only from a few different taxa across the food web. So for the horses, I have oxygen, carbon, nitrogen, zinc, and strontium. So lots of fun things going on. And I sequentially sampled all of them. And so if we start getting into the zinc stuff, so this is the food web. And the first thing that we see is that we kind of reproduce the trophic level groups that we're expecting. So we have the purple carnivores are the lowest, and the herbivores tend to have higher values. So this is nice. It works like we expect. Something to note is that hyenas are often intermediate between other carnivores and herbivores. And this is because they're bone eaters necessarily. So they like to crack a lot of bones. And because the bone, as I mentioned before, has slightly higher delta 66 N values, they kind of end up being in like a omnivore kind of niche. So this is all as expected and very nice. But what we also see is that we have actually a lot of structure within the herbivores. And so we see that things like cervids, which we traditionally would think that maybe they consume a bit more browse, tend to have a bit lower values than the horses, which traditionally we would think like, oh, they're probably more on the grazer end of mixed feeders. Don't ask me about the rhinos. They're always weird. If you want to know more about rhinos, talk to me at the coffee break. But so we're thinking like, okay, is there something going on with this effect that we see in plants where grasses tend to have higher values than tree leaves? And I want to introduce a little bit the data from the other isotopes so that we have we know what the situation is, what's going on. So just to note here, so this is the oxygen data, is that the pink is basically, so what I did is I sequentially sampled all of them, and then I picked the highest value for the summer and the lowest for the winter. So the pink is always the summer, and the blue is the winter, and the gray is the mean. So what we see is that and this is across time. So do I have a pointer? Yes, great. So this is the oldest data and this is the youngest data. So we see that we have quite a lot of change in the oxygen, and we have some really super low values here. These are some of the lowest values ever reported for MIS3 in Europe. Yay. So in the context of the site regarding what's going on with the hydrology, we're interpreting this as mostly reflecting temperature change. And this matches also timing-wise very well with some of the pollen sequences that we have from Western Germany, is that this falls into a stadial phase. So it seems like it's kind of getting quite cold in there. And then in the nitrogen, interestingly, we have very high nitrogen values at this time, and they kind of like peter out lower in the upper Paleolithic. And so, okay, nitrogen is very complicated. So if you have other ideas, let me know. But so I'm kind of interpreting this in a way that maybe it means that this cold phase might be quite dry, which is what would match the other kind of paleo-environmental records that we have, and that it's maybe then a bit wetter towards the end. And then in the carbon, to be honest, as the theme of this talk, not much is going on. But generally, it fits with a relatively open environment for Pleistocene Europe. And then, so then we have the zinc. And I've excluded this one individual based on the strontium values, just because we think it might be migratory. So I've just kind of chucked this out the window. But otherwise, what's quite interesting is that we, except for this individual, we see the highest values exactly in this kind of climatic excursion. And they also have the least amount of seasonal change. So we could kind of think like, oh, okay, if this is a relatively cold, dry environment where horses might be grazing more, this would actually fit with what we see also across the food web and what we see in plants. So maybe there's something there that we can do to look at grazing and browsing in Pleistocene herbivores. But yeah, obviously we can't test that with this data because it's archaeological data, but it would be consistent with this idea, and that's really interesting, I think. And so let's talk a bit about comparing this to other sites that we have, which is not many, but so we have one site that's a Spanish site. It's vaguely comparable in age. It's a late Pleistocene site as well. And here we also see kind of like the cervids seem to have slightly lower values than the equids. So there we also do kind of see this grazer-browser distinction. I would like to mention that we're pretty sure it's not related to ruminants versus non-ruminants because of the rhinos that I don't want to talk about otherwise. But so we think it's probably dietary. And then we also have published a modern food web from Cubifora in Eastern Africa, where we have the same trend, but unfortunately, here's the twist, is that there's also some data that a good friend of mine, Nicolas Bourgon, has been generating for his PhD working at sites in Laos, and these are also all late Pleistocene. And there it's quite complicated. So what we have to know about these food webs that he was analyzing is that there's a huge variety of different species. So I've grouped them here kind of like in bigger groups, but often these will include multiple species that we can't often identify. And so what he was looking at to look at this grazer-browser distinction was to say like, okay, here we actually have a C3, C4 environment. Do we see a correlation with the more traditional grazer-browser tracer of delta 13C? And we don't really, but also there's a lot of grouping going on in some of these taxonomic groups. And so in some we can kind of see like, okay, this is maybe more like what we would expect to see, but then in the caprines, it's kind of going more the opposite way. So it's not really clear why at these sites we don't really see this grazer-browser pattern. So it might be that it's just kind of obfuscated by really complicated different taxa that might have different ecologies that we don't know very well about. It also is the case we don't really have true grazers in these sites because it's a tropical forest. So it's generally a pretty closed environment. But I think we can see here mostly that there's a lot of structure in the herbivore data that I think there's a lot to explore more beyond what people have been using zinc for in relation to trophic level. And something else that I wanted to mention just briefly is that I think sort of like an alternative hypothesis that we're thinking about is, especially with this correlation between nitrogen and zinc. So here you can also see it correlates more moderately well over this data, is that there might also be an effect of the biogeochemical cycle in the soil, because we know that that affects nitrogen stabilizers quite a lot. And with zinc, that's probably also the case because we do have biogeochemical cycling of zinc in the soil. It's just the problem that at the moment, we know very little, like we have very little specific expectations of what that would look like in different climatic conditions, because most of the research in soil has been done on modern soils and people looking at agronomy who don't really care about this kind of stuff. But so this might be something that's going on as well. Yes, we have things like origin of organic matter that might play a role, things to look into in the future. I'm going to skip this because I'm running out of time. But yeah, I want to thank all the great people on my team and you for listening. Please ask me questions.